So basically, for everything you need for today's tutorial is just a one router and two bridge boards. So we are going to kind of show you how to set up it in a radar setup. So we are going to use one of the phased array as TX and the other one as RX. So for the bridge board, you will have one TX and one RX set up with each other. And you also need one control PGA. And this usually are all the hardwares when we ship them out. So we just so what we provide is just a router with the power PoE adapter and the bridge boards with the onboard connectors and the control PGA. So when we receive that, the other things we need to prepare are the micro USB cables, which is used to first to configure the control PGA. And second, you will need another one for each of the breadboard to power them up. And for other ones, for the baseband processing part, that is really depends on what kind of USFA or FDR you have. So basically, for our breadboard, you can just use SMA tables to connect. And I think that's pretty much it. I will show you some of the other details on how to debug the platform. But we do not have so many of these connectors, so I will just show you on this video with this camera. Right. So is everyone ready? Do you have the routers with you? So for the first part, you just need to have the router and the PoE adapter with you. Okay. Right. So for the PoE adapter on it, you can see that it usually says one as PoE and the other one has a LAN on it. So connect the cable, the port with the LAN to your laptop. And the other side is just the first little token. Right. So that is the first step. And for the macro take, let me see the box. So basically, we need one router, or we need a macro take router. So this is macro take one. You can open the tab, so it is just needed to be powered. And inside the case, you will see one of this adapter. This one is just you need one port is for powering, and the other one is for LAN. And what you need to do is just use the power adapter from here. This one connect this DC port to this port, so that it will provide the power to this adapter, and it will just power this router used through this Ethernet port. Let me show you the physical connection of it. So you just need to connect this port to this Ethernet port, and connect the other side of it with this DC power adapter, and just plug this to the wall AC port, and then it should be powered up. So you will see the light, it turns blue. And the other side is one, you need to have one Ethernet cable to connect to your laptop. So this is for MacroTech. And the other one, for the spare parts, this is the setup I'm going to show the demo for today. So we just need to have this router board. Do not power it up. Let's unplug the cable. So right now, what you need to do is just you have the router and this PoE adapter. Is this? Oh, right. So this is a power adapter. It has one as LAN and the other one as PoE. And for the LAN one, connect it to your laptop. And the other side, first, you just leave it open like this. I'm going to show the how to set up the hardware later. Right. Everyone ready? Okay, let's get started. So let's get started. So basically, our high-level idea of this project is turning the commodity multiple chain 802.11ad routers to a software-defined radio. So we have this is the reason why we're trying to hack or reverse engineer this Wi-Fi router, because we already have the phase arrays at this, and they are available on the market with mass production. So the cost of it are really low, comparing to all the other custom design phase arrays. So our whole idea is just trying to turn this kind of radio to the software-defined radio. So at the very beginning, we need to I would like to first share some of the details about these radios, so that you can have a more clear idea on how can we achieve this kind of target. So one kind of main difference between the millimeter wave setup with the previous microwave setup is basically on the antenna side. So for the microwave setup, usually they just have a baseband module such as a NIC-card like they shown over there. The NIC-card showing over there, it have all the baseband processing and the front-end radio with it. And then it is connected to another large antenna through these cables, coaxial cables. And all the signals being sent through the cable will be just the microwave signal. And basically, you will see this kind of routing with every kind of devices. For example, in the laptop, you will see similar kinds of connections. So what we are seeing right here is that the antenna usually they are just the passive ones, and but for the millimeter wave, this kind of long cable routing need to introduce a lot of attenuations to high frequency, especially for 60 gigahertz. And therefore, usually for the millimeter wave setup for the mobile devices, we will see that they are split the whole radios into two parts. The first one is still the NIC. It contains some of the analog front end and baseband processing part, and there will be also an active array. So for this active array, usually it is used for several different kind of functions, including it is an antenna array, so it will include the beamformer in it, and it will also act as a kind of a converter, so that the signal being routed between these two parts will not need to be very high frequency. So usually what we are seeing is that for most of the devices, either the 11AD, the 1 gig routers, or the Wi-Fi card, 1 gig cards, or the 5G NR radios, the ones being available in our smartphone right now, they are both having this kind of split setup. So usually they will route a kind of RF signal in between, so that the routing signal does not introduce too much attenuation for the routing. This leads to a kind of problem. Well, this gives us kind of the flexibility on converting it to a software-defined radio, because we are directly having the analog signal in between. So as long as we can hijack this channel, then we are able to send the kinds of arbitrary signal as we want. But the other thing is that we also need to learn about how the active phase array is controlled by these NICs, or say the baseband module, so that we are able to reconfigure the phase arrays as we want. Right. So therefore, we look back, taking into a detailed look on how the Wi-Fi card is being controlled by the systems. So if we want to have it to be functional, at the beginning, it is started with the support of the drivers. So here shows the software stacks to support the Wi-Fi card. It's starting from the user spaces. You have all the functions like the management, the host app, set it up as AP, or the IW, all the useful tools to check the physical configuration, and also the WPS applicant set it as a client can connect it to a router to AP. And then between the kernel space and the user space, there is a net link in between. So the link in between, they are just sending all the data or configurations through this link. And then there will be a config 802.11, and that one are just the kind of APIs and configurations so that for all the physical and link layer configurations are done with that. So this is just a very general kind of architecture for all the Linux-based systems. Windows or other ones, they are following similar kind of architecture. This kind of architecture is being finalized kind of around more than 10 years ago. And you will see basically every kind of Wi-Fi card are having these general higher layers up to the config 802.11. Lower than that, there are two kinds of implementation. One is the soft Mac and the other one is the full Mac. For the soft Mac, it is just to have a higher layer of the Mac layer implementation being done in the software. So there comes the Mac 802.11. So that one is having some configuration, doing some processing for the higher layer of the Mac. Mac. But for the lower layer ones, it is being done by the soft Mac driver. So this is usually provided by the merchandisers. Usually they have their own drivers, which includes the implementation on how does Mac 802.11 should connect or say control their hardware. So there comes the drivers. The drivers are usually act as a kind of interface between the software stacks with the hardwares. And there are another kinds of implementation as a full Mac. So it will have all the Mac layer implementation either within their own driver or included just on the firmware of the hardware. So usually for those kind of drivers, they usually just provide some of the control commands so that they mainly have the configurations to the hardware instead of doing the Mac layer processing on the software. So in our case, here I give some examples on the most popular Wi-Fi cards. So for Intel and Qualcomm, the Atheros ones, they usually following the soft Mac driver of the soft Mac architecture. So for the Linux kernel, they usually call it as Mac 802.11 kind of configuration. And the other ones, such as Broadcom, they have all different kinds of implementations, but some of them are just doing it in the full Mac. And the other ones, the WiGig, the WIL6210 is the one we are using. It is also a full Mac kind of architecture. So what their driver provided is just it provides a kind of WMI wireless management interface commands between this driver and the firmware, so that it can do all the configurations to the NIC. So basically what we, at the very beginning, what we have done is take a look on this driver and learn about how can we do the reconfigurations with the software commands so that we can do the reconfigurations of the NIC as we want. And we are trying to learn about which kind of configuration we can make use so that we can convert it into a software layer. So it is just this kind of interfaces are the ones we are kind of make use of so that we can make these WiGig routers be research platform. So even for the V2X setups, we also are using these WMI commands to do the configuration. All right, so with these WMI commands, we are building a kind of Python server. So that this kind of Python server, it is running on the router. So it is running just on this router. So that it is just monitoring the remote commands from the host PC. We will just using Python to send a socket package to send all configuration message to the router. And on the router, we will have the Python server, which is monitoring the port, collect the configuration. And then based on this, so the left side is showing what you will going to see when you run this server, and it is just keep monitoring this port. And you will also see some other informations. For example, the driver debug files. This is basically when you run most of the Wi-Fi cars, when the driver is up, you will see this interface is being loaded to some of similar directory. So this is the Linux systems, how they manage the hardware. It is kind of directory-based system. And you also see the PCIe devices as shown here. And then what you need to take a look for every setup you have at the very beginning. So for us, when we configure it, before we ship it out, I will usually make sure that these numbers are correct. But I still suggest you to double check whether it's correct or not. So there are two kinds of information which is important. First one is that the hardware version. We have 3 here. This one is showing that it is kind of Sparrow Plus. It will both work for this Sparrow Plus router and also for the MikroTik. So we just trying to check the whether the baseband chip is the one we want to use, but because they are using the exactly same kind of chip and using same kind of driver and firmware, so that they all will be identified as a Sparrow Plus. And the second one is a firmware version. We will ship them out with the version as a 6.2.0.40. So this is the one we are verified that it should work. For the other ones, we do not have any kind of guarantee because some of the function we are using is based on kind of memory dump from this exact version of the firmware. And then basically, you can just ignore the firmware patch. This is what we have done on our side. And then you will see that it is waiting for connection. It is waiting for the configuration from the host PC. So this is the Python server. So we have 2 kinds of version of it. This Python server, we have it being cross-compiled so that it should work both for the ARM, especially for the Sparrow Plus, this version, this architecture of ARM, and also for PC. So it should also work for, I think it is AMD64. So so that you can use exactly the same Python server both on the router, the ARM-based router, or any kind of PC. And we also have, but you need to have a Python 2.7, I think, version, Python 2 installed on this system so that you can use this Python server. And the other one is that on the MikroTik, we provide another kind of configuration because they do not have enough space to install the Python with it. So we kind of reverse compile using CPython so that it is packaged in a C-based package so that it will work pretty exactly the same as this Python, but you just need to load another kind of version to the temporary directory. And then basically our kind of hack or reconfiguration, it is applicable to every Linux-based system. For the either for the routers or for the PC, as long as you have the Linux with it. So basically, either routers like Sparrow Plus, there are 5 Sparrow Plus, the MikroTik 3 antenna versions of it, and also even for the Talon AD 7200. But that one, it is using another version of the chipsets that is only single antenna ones. So even for the MikroTik, you also see that they also have some of the radio 1180 radios which only have single antenna array. That one are using exactly the same chipsets as the Talon ones. So for those ones, they are using different chipset with the Sparrow Plus, but our tool, in fact, it works for both. Yeah. So for those ones, you should have the router and the driver being available on that, and you have the firmware for that. Our server should also work for those, but it is just you will only have one array being available. And the other ones, another kind of setup is that you can just unplug this. You can see on the Sparrow Plus, it is just having this NIC card on it. If you make any kind of problem, for example, the router board just does not put it up, you can unplug this NIC card and plug it to a PC. And with some reconfiguration, you can still have it work. Right. So the router board, it is unfortunately discontinued, but still you still should be able to have a kind of backup plan for this whole setup. And the other photo shown over there is a single antenna version. So you will just see that on the left side, it is another version of the antenna array, which is also integrated in the Talon motor. So that is a relatively smaller antenna array. It also have 32 antenna elements, but it is not configured as a UPA. So it is kind of an irregular placement on the antenna elements. So usually we just did not use those antenna array, but it also works for our setup. All right. So
question.
Yeah.
So is that antenna the one that you on the MCube website you have a link to where you can buy a replacement NIC, but then is that the antenna that you can buy from that same supplier?
well,
But like I was looking
checked
for
with that supplier. We bought the last two they have for this 8 type port version.
okay.
Because it is discontinued. So I think they will not have any other NIC card like this. I'm not quite sure whether this one is still available or not. So you can check whether it is still available or not, but I'm not quite sure right now.
Okay.
Yeah. So basically we have the 8 array version and the single array version. But the difference between these two antenna elements is that for this one, it will require additional power cable. You will see that here there are a red and black cable, which is providing a 5-watt power supply to this array. It's kind of that they will need some additional power so that it can be powered up to support most of the active components on that. Without this power cable, it will not work. So for the PC setup, you need to find out a way to power those antenna arrays. So either break up the red and the black cable, or build another power board, PCB board, so that you can use in the same interfaces to power them up. So there are some differences between the platforms. Here I just show the ones I have mentioned before. We have the Airflight one. This is the default one. What we have done and we have most of the experience with. And second is MikroTik one. we did verify that the configuration of how the configuration should work. But it has relatively limited number of the antenna arrays and limited the length of the cables. But if you already have the amplified routers, you can just disconnect the antenna array and plug this antenna array to that router. They are interchangeable. So the antenna array is being used in these first two routers. They are exactly the same. And the third one is that if you have the router that this is kind of likely because this kind of router, it is not that stable. It is kind of vulnerable. So for if you just play with this in some kind of way to that. So if you do not have it work anymore, there are two choices. First is get another MikroTik router. Second one is that just take off the NIC card and the phase array, and then plug it to a PC. It should also work. So for that one thing I need to mention is that you need to be careful about the kernel version. So the system of it should be higher than version 3.8 plus. After that, the driver should be integrated in the kernel, so you do not need to compile your driver anymore. Right now we are seeing a kernel of nearly 2.6. So, we do not, so if you just have a newer version of the PC, you do not need to worry about that. But what you need to do is to get two files from the either if you still have it ready, you can just compile copy two files. First is the firmware file, and second one is the BRD file. So that BRD file is the configuration, is the codebook file. So if you do not have any kind of working, just contact us, we will share it with you. So we also have the location, where should be this file's location on our website. You can check it on our website. So for this three setup, for the MikroTik one, you will need to use our recompiled CPI kind of packages. It is available on a separate page of our website. We have a link in our news. You just can click it on the MikroTik one, and inside there is around one page of the introduction on how to configure the MikroTik router. So you need to first install OpenWRT into it, and then we also have the packed version of the servers, so that you need to copy that server instead of the Python server to it to make it work as we want. So basically what you need to take care of the other two setup. One is that for the MikroTik one, you need to take care of the different version of the server. And for the PC one is that you need to figure out a way to power the antenna array. Right. So for the commands, we have some available commands as shown over here. These are the basic commands being WMI commands, which is being used. You can learn about how to use those if you want to have further flexibility on the configuration. But we also provided some scripts to just call this commands so that can be pre-configured as what we have shown. So the commands are available on the GitHub. You can just download it over there. And if you can see the requested input and get some helping information by running this help command. And okay, let's start with the demo. Let me okay. So people, people online, can you see the camera? have the router here, bridgeboard over there. And okay, so let's see. Let me also bring out. That's it. Let me also bring up the. Right. So basically, today I'm going to show it with the WSL from on the Windows, but it is just a kind of Linux terminal. So it should also apply for any kind of other terminals. What you need to do first is that you need to configure your even I haven't typed it in. So let's see. So first you need to first plug in your Ethernet port of the PoE adapter. For this one, you should see, you need to first configure the IP address of it. We need to make it work as a IPv for. So, basically, we need to configure the IP address of it to 129.168.137. Don't need to configure it to that subnet. Oh, I see. Yeah, I haven't plugged it into have an active connection in between, so the interface just did not show up. All right, so so you can plug in also the router right now. Yeah, so power it up. It should also initiate your yeah. So on the let me bring up. So for this router, you will see that there are three parts of it. This one, you can see that here, here, there is a kind of console set over here. And the right side one, there are PD over there. So we just plug the PoE adapter, the PoE port with this port, it will power it up. And the first, this light will turn as amber, and then it will turn into green. It will take some time, just wait for it. And after that, you should have the interface being available. So as shown here, I have interface here. And for me, on Windows, I just prefer to configure it in the control panel. Just have the IP address shown like this. You just need to put it inside the 137 subnet. You can just choose a random one, except 1 to 10, 0 to 10. So for all the routers that we have today, you can see that we have labeled the subnet IP address on it. So you need to, when you follow the following tutorial, you will need to use that subnet. Right. So for right now, you can just put as probably 100 or even 200. It should both work. And configure the subnet like this. And that's okay here. And then let me bring up the terminal. at this time, you should be able to see that the interface have the IP address being configured. And then you can first try to ping your router. So for me, I have about one. So you can change the IP address as the one label on your router. So you can see that I'm able to pin it. So basically this means that our router is being booted up. And then and the second thing is that you can try to SSH to it.
You can also
So
use the link to-
the user of it on it, you just have the root user, just run the SSH root and have it been connected. And then enter the password as a 1, 2, 3, 4, 5. And you will see the console. You have it right now. So if you are using relatively newer version, the keychain might not be compatible with it. This one has a relatively old version of encryption. But if you are using any version lower than 1.18, it should just work at this.
It's 1, 2, 3, 4, 5, 6, right?
Yeah, the password is 1, 2, 3, 4, 5, 6.
Okay. I'm gonna get you.
It's doesn't think that that's the right password.
Unless I'm doing the wrong. Name permission denied. Just page into this. Oh wait, no, it's root. Forgot root. Oh. Okay, cool. Yeah, it worked.
Okay,
Thanks.
Mac OS works for this.
It should also work.
Oh,
You just need to use the terminal to use, but I'm not sure.
can't
You may
find
need to use OSI.
Could you change the IP address for
because
internet?
I was using the Linux.
You're in, you never
tried
tried in
to-
Linux right now, okay.
No, I haven't checked it yet.
Yeah, but I can try.
Yeah, if you have SSH in the terminal, it should work.
Yeah, so that's.
The key exchange problem.
Oh, the keep string problem, I see. So I'm not sure whether I have it down. So basically, we are aware of that kind of problem. For on the website, we have mentioned that you need to support legacy in encryption algorithm. So you need to, when you try to SSH it, it will show you what should be, what of the versions.
Yeah, don't worry, I got problem solved from another computer. So
Okay.
I know how to solve that.
Yeah, I think we have some backup laptop. So you go back and take a look at I think you
You can find the internet?
Oh, close to the oscillator. There's a one. Okay, so we will get another laptop for you. Alright, so yeah, so basically what we have is just like this, or we already had you can SSH to it. So this kind of terminal I will just leave it here. It is just having SSH to the router so that you can have all the configuration on that. And the other step will be that another thing is that we will have the host command here. So basically you need to use Git to get the host commands from our website. So here I just have it in this directory. I have all the files shown over here. And then for our setup, for this tutorial, we will just start with the configuration. As here, we have several available Python kind of scripts. All these kind of scripts, they are being used to do the configurations. So you can see that we have the text mode, args mode, the log code book and read code books that are check arg status. And all these kinds of scripts, you can check the Python code so that if you want to use it individually, you can just use that. So it is just sending the corresponding commands to the socket so that you can send out this command from your host PC to the router. But we also provide some kind of scripts to simplify the configuration. We have the log code books script and also the setup server scripts. So basically on our website, what we showed is just after you have the router being booted up, you can just run the log code book message, and the first input should be 1. Here my IP address is 1, so I just put 1 here. You can put the IP address what you have on your side, and then it should be setup server. Sorry, we should start with the setup server. So for setup server, it will first try to initiate the Wi-Fi card. So when you run this, you can see the output like this. It's just an output after it run if config up. So basically, you can do it in both ways. On this side, you can also run if config 190 up. You will also see similar kinds of output. Let me press the comment. So if config up and run the config, you will see that this interface has been put up. So this is the first one you need to check. After you run the script, you should see that 190 is being up. Otherwise, you should unplug all the things, even the power, and check the connection. Usually in this case, if you run the message, you will see that this first interface should be ready. Firmware should be ready after 10 milliseconds. So for the message output, it is also useful for the debugging. So basically, what is important is on the version, on the firmware. So usually it shows what kind of file is being used for this booted up. So as you can see that firmware is this file and the board file is this file. So if you check it in the lab firmware, you will see these corresponding files. So you have the firmware and also the board file. So if you want to have any kind of you need to copy these 2 files to other setups, for example, on PC. But you may need to reconfigure to change the name corresponding. This file name, default file name, it's being configured by the driver. So for different version of the driver, they may try to load different name of the version of the files. So you may need to change the name of the file so that you can put it up as it is. Right, so here the first step is to boot up this WLAN interface, and then what you need to do is just a log code book. So for the setup server script, you will also be able to see that in the temp directory, you should also have a server being copied to this. So the setup server, one, it will first boot up the interface, and second, it will also copy the server to the temp. So So this one, it is mainly because in some cases, the router does not have enough space. And the server is relatively large. So we just copy it for every time it is booted up. So after you have this, you can just run the Python with this server. It will take some time for the first time, but you will going to see the output as I shown in the slides. So we have this server being set up.
Can I borrow a laptop?
Hmm?
Can I borrow a laptop?
You also want one? Can find another.
Yeah, maybe, and also this has a password, we are not.
What is the Linux version that the minimum or maximum version that can
Version of what?
the Ubuntu version?
Ubuntu version. So for lower than 18, it should just work as is. For higher than that, you need to configure the keychain, the encryption. Is and connected to as the video. It will be one of the
Yeah.
so it is.
Bridges I can't find people, so I probably need them.
You can you cannot find the table.
Yeah, it doesn't show.
And did you download the Git repo for the host commands? If you scroll up at the top of this. Yeah. This Git repo. You download that Git repo.
That's good. Let's see.
Maybe
You
try
can
different
find another laptop for you.
Maybe one.
Yes. We also try another adapter. Do you have other adapter for you? Ethernet. Let me keep going on to the tutorial. We will review this again later. So, all right. So basically, the next step is just doing the log codebook. So, for the log codebook, you will also need to input the first input should be the IP address, and the second one it is the IF module you want to use. By default, we enabled module 0 and module 7. I will go to the detail later on. But here you can just leave it open, like it work as a default ones. So basically, after you run it, it should trying to having a connection to the server. So for both sides, you will see some output. If you first start with trying to enable the corresponding RF module. And here you can see that the connected RF module, it is showing that which kind of RF module being connected to the NIC. So for the spare path, you will see that all 8 of them. But for the MikroTik, you usually can only see that 3 of them being connected. Usually it is 0, 1, and 5. And for the enabled IF module, this is a one set as the input. So by default is 0 and 7. So you can see that it is being enabled. And following on, it is trying to load the code book one by one. So here you can see that here are the parameters being loaded. By default, it will just trying to load the codebook as shown here. It is a 15bin.bat file. So this is the 15 bins. In fact, it is 16 bins, I think. It is 15 bins, but we are logging 16 bins to the router. So for these 15 bins, by default, we are providing several bins, which is have a equal kind of spacing from the -30 to -32 plus the 30 kind of angle, evenly distributed bins from one azimuth kind of plan. So I'll also go into the detail about how to do the reconfiguration later. But for this one, we are just it is just trying to load the codebook to it, and it is reading the bin from this file. So you can do the reconfiguration, try to change the files inside the logcode scripts. So you can check the logcode script and also the corresponding Python scripts it is using and do the reconfiguration for that so that you can load your codebook. So any kind of codebook you generated and load it using those. And basically that is, this is just several steps you need to do the configuration before doing the transmission. So here you will see that there are some outputs on both sides. This might be useful for debugging. And also you can check the check whether it is the codebook is being loaded correctly. So here I will just try to read codebook like this. First one is IPLJS, second one is enabled module, third one is TX or RX, and last one is the sector number. And here I'm just looking into my router with the 0 module, the RX and sector, and also for the sector index 0. So we can see that the magnitude is all 7, the phase is a kind of random one. This is after calibration, and the amp is all set as 6. This is the one we loaded, and we also see that we have, after read this codebook, it is being loaded correctly. All right, so this is basically all the steps you need to do for the configuration. All right, let me move on. And here, just is there any other kinds of questions so far? Okay, if not, I will just move on. Okay. If you have finished your attempt, just power this down so that we are going to try to do the hardware configuration. All right, so then let me talk about the module number mapping. So you can see that on this hardware, it has a number on these hardwares. So for the Sparrow class, you will not see any label on the NIC, but you will see some numbers on the antenna array. So it has a corresponding connection of these coaxial cables, and they also have a color label on it. And here are a kind of mapping between this antenna array and the NIC. These are the corresponding numbers to those phase arrays. But these kind of numbers, they are not exactly the same one being used in the software. So software, they have a different kind of number or index to it. So we call it as RFID number or the module number on software side. So for both the RFID NIC and also the MikroTik one, you can also see the numbers index over here, they are following the same kind of thing. For the reconfiguration on the software stack side, we need to follow another index. So there are another kind of mapping showing over here. So if you're just using the Alpha or Spiral Plus, what you need to take care of is just looking into the index showing this figure. So for any kind of connection, what matters most is just have the corresponding baseboard connection to the corresponding port, and that port is corresponding to the module number as shown on this figure. So for I have mentioned previously on when you are doing the load codebook, you need to provide the module number you want to use, and that module number is corresponding to this module number instead of the index provided by the hardware. And then, so for our scripts, you can see that for the load codebook one, the module number by default is set as 1 to 6, which is the sum of the 0 and 7. So it is kind of converting the bin map to the value. So you just, if you want to initiate the module 0 or 7, this is usually by default we are using these two because these are the two antenna arrays on the side. So this 1 and 7 are corresponding to module 0 and 7. And these two are having the longest cable. So by default, we just use those two as a default setup. And therefore, let me talk about how can we convert this router into SDR. So what we are doing is just insert this kind of bridge board in between. Just have it being connected in between through these quick cables. So as shown in this figure, we have the bridge board, have the BTU and control FPGA, and we have the NIC or baseband module on the one side and the phase array module on the other. So for the hardware we have is just the first thing is this bridge board. We have all the connections. So we have the these connectors, coaxial connectors to the baseband card, and on the other side we have this adapter port adapter for connected to the antenna, and also another SMA cable to the control FPGA. But let's go to the IMO for the hardware setup. Let me show the camera right here. So before doing any kind of hardware reconfiguration, first unplug the power. Unplug the power. Right. So here I have unplugged all the cables here, and we also have this bridge board. I have the TX and RX set up with each other, and you can see that this is coax cable, which has a JIC port, which should be directly connected to the NIC. And the other side is the adapter port, which is connected to the phase array. And these are the ports which should be connected to the control FPGA. So for the hardware reconfiguration, you just need to first unplug two of the cables, as shown here. Here I just unplugged the one which has the black label on it, and the other one is the one with the purple one. So for all you have, it may have some glue of it. Just gently lift it up and transfer the glue and remove these two ports of this cable. And then what you need to do is that here you have this JIC cable, connect it to the NIC board. Just have it, line it, and push this port.
Doesn't matter the order, which one is which.
It doesn't matter that much. But right now, I would suggest well, what matter most is on the control PGA side. So, for the NIC, what it is doing is just doing the configuration of doing the initiation for the phase array. So as long as you enable the module and load codebook, by doing load codebook, the script we provided is load both for the codebook for the TX and RX. If you have different frame configuration, the connection on this side, you need to be careful about that because you need to know which module you are using for which antenna array. So for right now, I just have one of it connected to this one port of it. Just align it and push it down. You should hear a small click to it when you connected it, and you can just turn it, and make sure that it is just not popped up. And the other one, you also connect it, align to the ports, and push it back. So for this side, you just have this connection. So these are the connectors to the NIC with the pre-board. And for the other side, you have the antennas connectors. And here I just have these two connectors up so that I have enough kind of length of cables. I think you should be able to. So all these antenna arrays, they are interchangeable. You just need to make sure which one is connected to which breadboard, and you are going to use that as TX or RX. And just also similar to the previous one, you just need to align this cable with the port and connect it. Right. So if you want to, that's from you can. Oh, I should.
I got my thought because I don't have flags on here.
So the cable length is a little bit limited, so you may need to adjust the direction on the board.
This, what we're gonna do is put this one attach here and then that one attach with one of them. Get it like. Stand it up. Just let's see. Eventually this will have to be sitting on the table.
Right. So for the very beginning, you can just follow the steps, but after you have the setup being ready, I would suggest you to use some of the heat glue to protect those ports because it is kind of vulnerable and all these ports, they have a limited life on the number of plug and unplug. So all these ports, I would suggest you, especially for the GSC port, I would suggest you to use some glue to just glue it up. And then for the other side, you will see that there are two of these connectors, and you just need to connect it to this control PGA. Right. This is basically our setup.
Yeah, you kind of have to move it out of the way.
Okay, so in fact, for your setup, you can try to reconfigure the hardware location, especially for this phase array. You can just move it from the front panel and have all the cables be if I can show you more clearly. So because we have some kind of limited length of the cable, you can just remove this array from the front panel. There are some screws, you can just pull it off and then unplug, remove this first panel of the antenna arrays from the front panel and have all the connections and move it to the back side so that you have more flexibility on the Right, so basically this is the hardware connections we are going to have. And for this kind of bridge board, you just need to connect all the SMA port to your USRP or any other kinds of SDR. You can be used as just a single-ended one or have an IQ input so that you can just use it as a baseband one or low app. And for the control FPGA, we can just use it to set it up, to have a real-time configuration of the table. Any questions so far? Well, during breakup, we can.
There's no order on this one. Any of the ports are fine.
Yes, yes. It is just you will need to do some reconfiguration on the control commands of the on MATLAB control disk to complete this FPGA. All right, so for this control FPGA, in fact, so previously in our server, we also provide some of the commands, especially the TX mode and RX mode commands. They can be used to configure to change the bins, in fact. But it will introduce some not controlled or uncertain delay, system delay on it. So it cannot be used for real-time beam swapping. This is the reason why we introduced this control FPGA. So for this control FPGA, by default, we have this prototype board and have 4 SMA port being populated. So for all this port, we have the port number as the 4, 5, 6, 7, 8. But on the other side, we also have port 1, 2, 3, 4. So if you want to have more antenna arrays being configured by one control FPGA, you can also populate other SMA ports to the other side. But make sure that you have connected the 2 ports as shown on the back side of it. We have one as a signal and the other one as the ground. So if you do not have a grounded one, if you not have a good enough signal quality to do the configuration. But anyway, by default, all the control FPGA we shipped, all these 4 ports, 5, 6, 7, 8, they should work as it. So as long as you connect it to the whole hardware setup, you should be able to configure the front end relatively stably. But as we shown in our website, all the configuration sets, it should follow specific steps. So for the initiation, you should follow all the initiation script using the scripts we provided before you power up this control FPGA. Because this control FPGA, it will send out the configuration in kind of loop. So periodically, so it will interrupt all the initiation commands you have through this to the router, to the phase array. So basically you should first follow all the scripts which will do all the initiation, configure which of the antenna array should have the corresponding code books, and then you plug in, power up this router to the control FPGA, and it will sense out the real-time beam swapping commands to all the phase arrays, so that it will go through all the beam swapping. And also you can see that there are some trigger inputs over here. So for this hardware, there are 2 trigger inputs, which is going to use to synchronize this control FPGA, the signal commands, and with the USRP or any other kind of software defined. So that's when the software defined radio sends doing the transmission and receiving, it can send out a trigger signal to this control FPGA, and then the control FPGA will use that time as a starting point to send out all other control commands or beam swapping commands, so that we can synchronize beam swapping with the sampling of the software defined radio. And we also have the flexibility on the hardware, on the antenna base. So basically we have study on how this phase array works. So here shows the number of the antenna elements index, and also we have a coordinate system shown like this. So we provided MATLAB scripts, MATLAB codes on our website. You can use that codes to do the reconfiguration, to generate your beam. So for that code, it is following this coordination. You can generate the angle based on this coordinate and generate the codes with that MATLAB codes. And then some note about the carrier coherence. So if you wanted to work as either a radar or a MIMO system, you need to have multiple phase arrays to have a coherent carrier, so that you will have a coherent phase difference in every transmission. So in the hardware, what we have the baseband module with all the phase arrays connected on the same. If you have it connected to on the same baseband module, all the LO, or say the reference clock, they should be synchronized. So that all the phase array module connect to the same baseband module, they should have the phase coherency among all the carriers. But you also need to be careful on the BPU side. So you also need to have the carrier on the BPU side to be phase coherent. This, yeah.
I'm a little bit confused about the baseband module and then the BPU that you mentioned. I think in some of the systems they are, as far as I know, they are the same, right? It's like, for example, a SDR, USRP device, they are in your system, is that referred as the baseband module?
Well, we are calling as a BPU, but in fact we have 2 kinds of configurations. First one is that we have, as you can see here, there are 2 ports here. So you can configure as a homodyne architecture, feed I and Q to these 2 ports. And you can just have exactly baseband samplings. This is kind of set up exactly for very high speed baseband processing units, such as RFSoC. So we have around 2 or even 4 GHz sampling rate. And that one is exactly a BPU, baseband processing unit. And the other one is that you can just use 1 part of it and use this as a second stage of the heterodyne architecture.
So basically in this setting, like the IQ is already combined, right? As the real and
Yes. Yes. So you can just use a software defined radio, have a first stage of up converter on it, and set it up as around 2.4 or 3 GHz, so that you can get rid of the image of that signal.
So the output from the USRP is already modulated signal
Yeah,
on
it is.
on the
Okay.
oh,
So in that kind of case, for the heterodyne architecture, you need to make sure all the carrier signal from the BPU, they are phase coherent. So in different setup, it may true or may not true. You need to check the, for example, USRP, their website. Some of them, they can have phase coherency between different setups, especially for the X series, they have a phase coherency between different devices. For B210, it has two of them being phase synchronized. For N310, although it has four interfaces, but they are not phase coherent between two dot boards. Yeah, that is a kind of problem. If you just initiate it and does not reboot it or have a reconfiguration on the LO, then it might be fine. So you can just if you just set it being continued, just have one time carrier configuration, LO configuration on that SDR, and then just let it running. It will keep the carrier offset over there, and you can just do transmission and use all the signals you got to do over the air phase recalibration. But for other kind of setup, as long as you reboot it, all the BPUs, you need to do a one-time of phase calibration. Okay. Yeah. So this is one thing you need to be careful about for the carrier coherence. And therefore, the next for the next step, let me briefly introduce some of the GPIO configuration. For the USRP ones, we have X3 series and 3 series. They have the GPIO on the left side and on the front panel. So it has they have their index on it, and they also have a mapping between this GPIO and the control, the UHD control. So we are using the automatic transmit and receive function of the UHD so that we can use it, set it up, and when it has any kind of transmission or receiving, it will send out a trigger signal outside from this GPIO. And we just need to connect this GPIO to our control FPGA so that we can feed the trigger signal to the control FPGA. And for the B210, you can also find another GPIO inside of the case. So there are a GPIO inside so that you can send out the trigger signal from them. And there are also WARP also have this kind of function they use to be used to synchronize multiple warp boards, but it is just a sense to synchronize multiple warp boards. You can also use those specific GPIO to synchronize with this Fentra FPGA. And this is the last slide of it. We can have some platform extensions of our hardware. So in fact, because we are specifically designed our hardware with these off-board connectors, so you can try to have your custom connections so that if you want to support different kind of architecture. Here is another kind of example on how can we provide external LOs to the bridge board so that we can have a better performance on the phase noise, such as phase noise or communication performance. And also you can try to have just one or multiple baseband units to just use the baseband units as an initiator. So in this kind of case, you can use the F port or the I port from this NIC or multiple NICs, or even for the single chain version of the MikroTik routers, because they are just act as a initiator. What you need to do is what you are using it is just sends out the initiation commands, doing the log code book, and you can just leave it like that, leave it there. And all the other phase arrays, the LO, they're providing from here, we are showing the LMX 2595. That one is a LO or a PLL or frequency synthesizer from TI. You can just use a kind of evaluation board of them so that you can synchronize multiple of the bridge board, providing cleaner LO and also fit it to the PON phase array module, so that you can kind of have a setup with larger kind of antenna array, and also have a better performance of better performance of the configuration. And also we can set it up as a radar, as I mentioned here. In fact, our hardware we are providing today, it can be set it up as a radar setup. So but in this case, you will always need to use this control PGA to set the TX and RX, or set it to TX and RX, or set the phase array on the same, connected to the same NIC to TX and RX, because the control commands from the Python server cannot configure it like this. We will need to use the control PGA to set it up as a radar setup. And also you can have it as a larger array and a phase array. For example, have multiple of the routers, have the phase array being frequency synchronized from external clock board. And all of them, they can be frequency or LO, share the same kind of LO, so that they can frequency synchronized and also have a coherent phase. So you can generate even larger antenna array. So that pretty much it on my side. It takes more time than I expected. And this is
You want to say something about something we need to take care of when doing experiments, for example, the thermal issue.
Oh, I see. Yeah, so there are something we need to take care of. If you are using our USRP code, it is not that working, but it just works for some of setups. Our USRP scripts, inside it, we have a system command calling to call for the Python scripts of the disabling the phase array. So this one is that command is used specifically in our testing for our paper. We are trying to disable the phase array anytime we are not sending out any kind of signal, because it indeed generates a lot of heat. So basically, if you are using the control PGA and set it to a specific beam, it will just activate all the active components for both the transmitter or receiving, the PAs, mixers, all the amplifiers, so that it will generate a lot of heat. So this is a kind of reason why you see that they have this kind of heat sink as shown here. And if you take a look inside of the MikroTik router, they also grew it to a heat sink. For this heat sink, it's kind of fine. So if you're just using this heat sink, you can try to use it for relatively long time operation. But when the temperature goes up, it will introduce some of the problems. First one is that the amplifier gain kind of reduced. So you need to apply additional gain on the baseband side. And second is that it will introduce a higher noise, both on the phase noise and also on the thermal noise. So it will somehow affect the performance of the configuration. But still, this kind of phase array, it is a kind of old product. The phase noise performance is not that great. And also it has limited the number of the control on the antenna gain and for each antenna configuration. For example, it only have one bit of the antenna gain control. It is basically turned on and off of each antenna element or a group of it. And also for the phase control, it only have two bits for it. So basically 0, 90, 180 or 270. So these are some configuration limitation on the phase array. So in fact, we are looking into the next generation of this hardware. 11AY routers are out, but we are meeting some problems on doing the kind of reverse engineering of the hardware. So what we are expecting is that they are using exactly the same kinds of driver, but we do not have access to the firmware and the port file. So that we will still need to look into whether we can have a flexible reconfiguration on the phase array. And basically what we are just reusing their phase array. So if we can figure out how to do the initiation and learn about how to generate the corresponding beams, then we can convert our current setup to the newer version of it, because basically they should follow exactly the same kind of hardware connection and also similar kinds of control commands. Any other things in mind?
Any other question?
So with the transmitter and a receiver right now, are you able to do the bit transmission connectivity, or just to get some physical parameters? Like you send a stream of the data from the transmitter, are you able to receive that? Using USRP, for example.
Yeah.
You can do that.
Yes. So we can use so at the very beginning, in case of simplicity, we just use the same USRP for both TX and RX, even for the 2 nodes experiments, because synchronizing multiple USRP it is a little bit hard. So at the very beginning, I would suggest to start with using same USRP for both TX. Yes, B210 it is much easier compared to N310. So for the newer version, either N310 or X4 series, most of them they have a newer version of it. They have integrated the Linux system inside, and they need to have the kinds of version of the kernel being paired between the UHD and the system inside. That is really hard to use. But for older version, the N210, they have a fixed version of the FPGA. For B210, it will just load the FPGA image for every loading through the USB. So for those ones are much easier to use.
Did you feel any need to use an external clock with your USRPs?
Usenix kernel clock.
Do you use a GPS discipline clock or just run without an external?
I see. So if you want to have multiple USRP to be synchronized, that might be needed.
or for greater frequency stability.
For frequency stability, I don't think it is that necessary. Yeah, but if you have multiple devices for both TX and RX, there are multiple resources for the carrier frequency stability problem. First one is that if you are using multiple routers, for it is generating LO by itself. So for that one, it is not that stable. So that is the first source of it. If you have multiple devices, you will see that the carrier frequency offset between different router, they're relatively large and they're drifting. They're drifting basically because of the temperature.
Right.
And if you just have a GPSDO on the USRP, it will not help that much because the CFO is mainly introduced by this carrier. But you can try to introduce external. Okay, you can just use similar kinds of architecture like this. Use external LO so that you can try to synchronize multiple clock from multiple LOs like this.